We're going to have a little bit of a look further at constraints that we need to satisfy in the shooting method. First, however, it's worth pointing out that there's more than one way to shoot in the shooting method. So what we did previously is we had some boundary condition on the right-hand side, and we needed to choose something on the left-hand side to satisfy that. So that's one way of shooting. It is also possible to start our integration on the right-hand side and integrate left. In other words, using a negative step size to go back to the initial condition. There's nothing wrong with doing that. The other way of shooting is you can actually shoot from both ends. So for example, we know we need to satisfy this here, but we don't know what the starting point is, and we don't know what the derivative at the right-hand side is. We could make a guess for the derivative here and a guess for the starting position, and then integrate to some central point. So we're integrating one forwards and one backwards, choosing different values, till eventually we meet in the middle. So it is also possible to shoot like this. So let's have a look at constraints. Constraints are a very, very important part of the shooting method, and they're often something that is tricky to figure out because it's always based on the particular situation that you're looking at. We're going to look now at the pipe flow of an incompressible shear thinning fluid. A shear thinning fluid is one in which the viscosity depends on the strain rate. So there's a section of our pipe. The equation that describes the fluid flow is that equation down the bottom left. 1 on rho dp dz is equal to negative 1 on r d by dr of r eta dw dr, where eta is our viscosity. The boundary conditions that we know are the velocity has to be equal to 0 at the pipe wall, that's r is equal to a, and the gradient of the velocity, dw dr, must be 0 on the axis. That should actually be equals to 0. So we're going to assume that the pressure gradient is constant, so dp dz is equal to some fixed value negative q. And our velocity field is going to look something like that. It's 0 at the wall, and it takes on some value in the center where the gradient across the center line is 0. We don't know how big the velocity is on the center line. That's unknown. It also turns out then, for the particular kind of fluid I'm going to look at, that for a power law fluid, the viscosity as a function of r is equal to eta as a function of the strain rate, which is dw dr. So the viscosity has some profile that looks like this plot here. Higher in the center, lower near the walls. So let's take our original equation, where we replace dp dz by q, or negative q I should say. Then let's expand those terms out to get this second order ODE. It's a second derivative term and a first derivative term. There's no linear term in this case. Because we can't solve a second order equation directly, we're going to have to split it into a system of two first order equations. So let's let y1 equal w and y2 equal dw dr. Therefore, dy1 dr is equal to dw dr is equal to y2. So that's our first ODE. We then need to take this ODE and write it in terms of y1 and y2, and it turns out it only depends on y2. dy2 dr is equal to negative 1 on eta to eta dr plus eta on r times y2 minus q on rho eta. Now eta is a function of dw dr, but dwr is just dy1 dr, and dy1 dr is just equal to y2. So eta is also a function of y2. So these are the two equations we need to solve. What are the boundary conditions? That is, the constraints that we need to satisfy. Well, we've already been told that the velocity at the pipe wall is equal to 0, and that the gradient of the velocity on the axis is equal to 0. So in terms of our variables y1 and y2, that corresponds to y1 of a is equal to 0 and y2 of 0 is equal to 0. We know that these things must be true. So what are potential adjustable parameters? In other words, what requires the root finding? Well, we don't know what the velocity field is on the axis, or sorry, what the velocity magnitude is on the axis, so that's unknown. We also don't know what the velocity gradient is at the pipe wall, so that's another unknown. So either of these either of these two things could be adjustable parameters. In terms of y1 and y2, that corresponds to y1 of 0 and y2 of a both being unknown. So we need to try and figure out how we're going to do this. We don't need root finding for both of the adjustable parameters. Okay, we only need to do it for one. So let's assume we're going to integrate from r is equal to 0, the centre line, to the pipe wall. So if we do that, we know what y2 of 0 is equal to. It's equal to 0. But we don't know what y1 of 0 is equal to. So that's an unknown. We know that the condition we must satisfy at the wall is y1 of a is equal to 0. That's that condition up the top there. So therefore, it seems like these are the things that we can use, and this is the thing that we don't know. So this then becomes our adjustable parameter, y1 of 0, in other words, the velocity at the centre line, and we do the root finding problem for this. It turns out that the other adjustable parameter, y2 of a, comes out in the wash. We don't ever need to worry about it. In fact, it's unnecessary. And if you think about this logically, this is a second order equation. You should only need two boundary conditions to uniquely specify the problem. We start off with these two here, but we then try and find out what this one is to satisfy the problem.